So far in our unit on thermochemistry, we have learned about how energy changes over the course of a chemical reaction from the energy of the reactants compared to the energy of the products. That's what's known as enthalpy. The change in those energies is called enthalpy. But what we haven't talked about is whether or not those chemical reactions will always occur. If you put two chemical reactants together, will they spontaneously react? Well, to answer that question, we have to not only consider the change in energy of a reaction, we also have to consider the change in what's called entropy. So there's three scenarios regarding the question, do chemical reactions always occur? A reaction can be spontaneous, meaning that the reaction, once it's started, proceeds on its own without additional input of energy and goes to completion. Right? So an example here would be like lighting a match. Right? Once we got it started by the strike on the box, we see that this proceeds on its own without any additional input of energy. And eventually, when the wood is all burned away, we say that it goes to completion. All the fuel has been used up. So that is a spontaneous reaction. A reaction can be, so lighting a match, I guess, is what we can use as our example here. A reaction can be non-spontaneous, meaning the reaction will not proceed on its own without a constant supply of energy and therefore does not go to completion. Right? So here we have a beaker of water. Here we have a piece of aluminum foil. If I put that aluminum foil in, that reaction will not spontaneously happen. Nothing will happen. Aluminum will stay aluminum, water will stay water. Right? So two chemicals put together, not spontaneously reacting. So here we're just saying aluminum and water. Now we can also say that a reaction is said to be at equilibrium, which we haven't really talked about too much yet this year. We will be talking about it in a future unit. But the basic idea of equilibrium is that a forward reaction is happening, but the reverse reaction is also happening. So the reaction starts, then the reaction slows down and appears to stop. However, the reverse reaction has also begun, and therefore both the forward and the reverse reactions are happening simultaneously and at the same rate. So that's something that might be a new concept for you at this point, but that happens for not all reactions, but some. So we say at equilibrium, both the forward and the reverse reactions are spontaneous. We'll be coming back and talking about equilibrium in the next unit, or actually in 2 units from now. So whether or not a reaction is spontaneous depends on 2 factors. It depends on enthalpy, otherwise known as the delta H of the reaction, the heat of the reaction, and entropy, which combine in a predictable way to determine if the reaction is spontaneous. Okay, so let's review what we know about enthalpy. Enthalpy is otherwise known as the change in the energy, right? It is the amount of heat energy either absorbed or released in a chemical reaction. If it's a positive number, it means the reaction is endothermic. And we say that there is an increase in enthalpy, right? Basically, when we had a potential energy diagram that looks something like this, from the reactants up to the products, that is an increase in enthalpy. A negative delta H means the reaction is exothermic, and we say that there is a decrease in enthalpy, right? So this is where we had a potential energy diagram that looked like this. The reactant started high and ended up with the products low. That's a decrease in enthalpy. Okay, so that is a review of what we've been learning about so far. Now, how we know or how we can recognize that an exothermic reaction is happening, right? We already know if there is a negative sign in front of the enthalpy value. We also know from the shape of this potential energy diagram where the reactants are high energy and the products are low energy. Or we know when the energy term placement is on the product side of a chemical reaction, right? So this is a product. Energy is produced. How we can recognize an endothermic reaction is there is a positive sign in front of the enthalpy value, or the shape of the potential energy diagram where reactants start low energy and products start high, or the energy term placement is on the reactant side of the chemical reaction. This is a reactant because it's on the left side of the arrow. So that's a couple different ways that we can recognize whether a reaction is endo or exothermic. Okay. Now, exothermic reactions are said to be favored by the universe, and exothermic reactions tend to be spontaneous. They are not always spontaneous, but they tend to be. So we say that the universe favors that those reactions are going to happen. Endothermic reactions tend to not happen spontaneously, so we say that they are unfavored. So endothermic reactions are unfavored by the universe and tend to be non or not spontaneous. Okay, so that brings us to entropy. Entropy is going to be symbolized by a change in S. I know this doesn't make any sense. There's no S in the word entropy, but that's the conventional symbol used for entropy. It's a change in, we would read this symbol as a change in entropy. Okay. And entropy is defined as the change in the disorder of the system. Okay. So the more chaotic a system becomes as the reaction progresses, the more entropy the system contains. So to figure out if entropy is increasing or decreasing, you need to consider what's happening by comparing the products to the reactants. If you see a positive delta S, that means the reaction has increased its disorder, which means it's become less orderly, more chaotic. A negative delta S means the reaction has decreased its disorder, meaning it has become more orderly. So that's kind of a twist on your brain to think about sometimes. But it's a positive delta S means more disorder. A negative delta S means less disorder. So that double negative gets a little twisty in the brain. Okay, so let's see how we can identify examples of increasing disorder, a positive delta S. Okay, some of the things you will look for, anything phase change going from a solid to a liquid, or a solid to a gas, or a liquid to a gas. All of those phase changes in that direction, in that endothermic direction, is becoming more chaotic, more disordered, right? Because you start with a very orderly solid to liquids to gases becomes more chaotic, more random, and definitely less order. So this is all a positive delta S as we go in that direction. The other thing, another way to recognize increasing disorder is if you dissolve a solid. If you take a solid and you add it into some water, and you end up with two particles that are both aqueous. So if we take a closer look at this diagram, this is a little small to take a look at. But what we have here is, here's your solid, and then here it is dissolving. Here is solid number 2, and here it is dissolving. Okay. So this is actually a graphic showing you more than just dissolving. We have solid number 1 added to water and the particles separate. Solid number 2 added to water and the particles separate. Here they're showing where those two aqueous solutions mix, but what we are looking at is those two processes separately. The dissolving of the solid into water, the particles get spread out and more random, more disordered. So one way of discovering if a system has become, has increased its entropy is to look at the state of matter as it changes from the reactant to the product side. But a second thing that you're going to look for is inspecting the coefficients of the balanced equation, comparing the reactants to the products. So if you are starting on the reactant side with few particles, and you end up with more particles on the product side, right, by counting up the coefficients, then that is said to be an increase in the entropy, the change in the entropy. So if we take a look here, right, here's our reactants. We have 2 total moles of particles on the left side. And on the right side, we have 2 plus 1, we have 3 particles on the right side. So 2 particles turning into 3 particles means that we now have more particles floating around in a container, which is more disorderly. The more particles you can have, it's going to be more disorderly. So increase in entropy. So now consider the opposite processes, right, which would lead to a decrease in the disorder, a negative delta S, a decrease in the phase from a gas to a liquid or to a solid, anything in that direction, or the opposite of dissolving, which is precipitation, where you have 2 aqueous ions forming a solid, one solid particle. Or if you have a decrease in the number of moles from a reactant, and like say, for example, 3 moles of reactant to 2 moles of product, okay, adding up the coefficients. And so it turns out that reactions tend to happen if there is an increase in entropy. We say that the universe favors the chaos, the universe favors an increase in entropy. And so anytime you have an increase in entropy, we say that that's favored by the universe, and those reactions tend to be spontaneous. Therefore, a decrease in entropy is said to be unfavored by the universe and tend to be non-spontaneous. So qualitative practice with predicting spontaneity. The first thing you're going to want to do is identify the sign on both your delta H and your delta S. That's going to help you determine the favorability of each of those factors, the delta S and the delta H. You'll then draw a conclusion. Are both of those favored, right? So the favorability we said is a negative delta H is favored, and a positive delta S is favored, meaning, so if they are both favored, the reaction is said to be, that's a typo there, is always spontaneous. If you have a positive delta H and a negative delta S, right, so they are both unfavored. This is an endothermic, and this is a becoming more orderly. That reaction is never spontaneous. But what happens when one of the factors is favored, but the other is not, right? Well, the answer to that question is the reaction is sometimes spontaneous, and sometimes it is not spontaneous. The reaction is therefore going to depend on the temperature of the reaction happens at. Okay. So that's going to be, we'll talk more about this in our lesson in 10.7, but that's the answer that I'm going to give you at this point in time. So let's take a look at a couple examples and try to figure out if we can figure out the question of spontaneity. So our first reaction that we're looking at looks like a combustion reaction. We have a delta H that is negative, right? So our delta H is negative. And which means it's exothermic. Is that favored? The answer is yes. Exothermic reactions tend to be spontaneous. We say that that's favored. But now we have to look at this reaction and decide, is this reaction increasing in disorder or not? So let's take a look. First thing I'm going to look at is the phase. I have a liquid and a gas for reactants, and I have both of my products as gases. So just looking at the state of matter, that is becoming more chaotic because we had a liquid as one of the reactants, and then we don't have any liquids here on the right, on the product side. Okay. We also have that's a 1 plus 3, that's 4 particles on the left versus 3 plus 2, 5 particles on the right. So this is an increase in disorder, whether you look at it from the state of matter or from the number of particles. So yes, that is also favored. It's a Y for yes. So both favored, we're going to say that this reaction is always going to be spontaneous. Okay. The second reaction, we see the energy term is on the left side of the arrow. So this is endothermic. So this is not favored. The enthalpy is not favored. Let's take a look at the entropy. Okay, so in this case, I have 2 gases on my reactant side of the equation, and I have gas on the right side of the equation. So with state of matter, everything's a gas. So let's just take a look at the number of particles. On the reactant side, I have a total of 3 moles of particles, and on the product side, I have only 2 moles of particles. So this is not an increase in entropy, this is a decrease in entropy. It's becoming more ordered, so that is also not favored. So we are going to say that this reaction is never spontaneous. Let's take a look at our third reaction. Okay, we see that it is endothermic, so it's delta H is positive. If we take a look at entropy, I have a solid turning into 2 dissolved ions. So that is a positive delta S. So here I have my enthalpy is not favored, but my entropy is favored. So if one of these factors is favored, that means that this reaction will be spontaneous sometimes, depending on the temperature. And again, we'll come back to that in our next lesson. Our fourth reaction, we have, we can see here that it is a negative delta H. It is exothermic. So the enthalpy is favored. But we can see here we start with a solid and a gas as reactants, but our products contain only solids. If we also take a look at the coefficients, we have 7 particles of coefficients, 7 particles on the reactant side and only 2. So this reaction is becoming more orderly, okay, which is the entropy is decreasing. That is not favored. So when one of these factors is favored and the other is not, we say that this is sometimes spontaneous, depending on the temperature. Okay, so we're going to take a closer look at this sometimes spontaneous example, and we're going to take a look at melting snow or melting ice. Okay. Melting ice can be shown as a chemical equation where you have a solid water adding some energy to make it turn into liquid water, right? So here's your ice, your snowflake. This is your solid water. And this is your liquid water, right? So this is H2O solid, and this is H2O liquid. Okay. So what do we know here? Our delta H, being on the left side of the equation, is a positive delta H. We know that this is endothermic. So this reaction is not favored. The enthalpy is not spontaneously likely to happen. But we see here that we're going from an orderly arrangement to a less orderly arrangement. So we would say that this entropy is increasing. It's becoming more disordered. And that is favored, right? So here we are saying that this reaction will sometimes be spontaneous and sometimes not. And so you can probably see here that snow turning into or melting into liquid water will be spontaneous at high enough temperatures, right? So this reaction will be spontaneous. This will happen automatically as long as the temperatures are above 0 degrees Celsius. This reaction will be not spontaneous at temperatures below 0 degrees Celsius, right? So this is what we're talking about, that these reactions can be spontaneous depending on the temperature. So this discussion about temperature's effect on reaction spontaneity continues into the next section. But for now, just to recap what we've talked about, the big lesson here is understanding what entropy is. Entropy is a measure of disorder, and that the universe favors reactions that become more disordered. And that entropy and enthalpy, the delta H and delta S, work together to determine whether or not a reaction will be spontaneous. That's it for this lesson. We'll see you back in the classroom.